Welcome to our exploration of angular kinematics in human movement, focusing on the fascinating concept of the instant center of rotation. In biomechanics, understanding how our joints move is crucial for both clinical and engineering applications. Today, we'll dive into the knee joint, a complex structure that doesn't behave like a simple hinge. Instead, its center of rotation shifts as we move. This lecture will guide you through the basics, practical examples, and the technology used to study these dynamic centers. Let's begin by defining what the instant center of rotation really means in the context of human movement. Instant center of rotation, often abbreviated as ICR, is the precise point around which a joint rotates at any given instant. Unlike a fixed hinge, the ICR can move as the joint flexes or extends. For example, when you bend or straighten your knee, the center about which your lower leg rotates isn't stationary. This moving point is essential for accurately describing joint motion, and it forms the foundation for understanding more advanced biomechanical concepts. Let's look at how this applies specifically to the knee joint. Knee is often thought of as a simple hinge, but in reality, it's much more complex. Its structure allows for both rolling and sliding motions, which means the ICR is constantly shifting as you move. This dynamic behavior is what makes the knee so versatile, but also challenging to study and replicate in prosthetic devices. Understanding the path of the ICR during knee extension, for example, reveals how the joint accommodates different types of movement, ensuring stability and flexibility. Biomedical engineering students, locating the instantaneous center of rotation in the knee can seem daunting. However, the concept is straightforward. At any instant, the ICR is the point about which the lower leg or shank rotates. As the knee flexes and extends, this point moves, reflecting the complex mechanics at play. By tracking the ICR, we gain valuable insights into how the knee functions during everyday activities like walking or running. Think of the ICR as the hinge point your leg is rotating about at any given moment. Unlike a door hinge, this point isn't fixed. Instead, it travels along a path as your knee bends and straightens. This movement is crucial for understanding joint mechanics, especially when distinguishing between rolling and sliding motions. Recognizing the ICR's path helps engineers and clinicians analyze both normal and abnormal joint function. Identifying the ICR is more than an academic exercise. It's vital for designing prosthetics and orthotics that mimic natural joint motion. By understanding how the ICR moves, engineers can create devices that better replicate the body's biomechanics. Additionally, the ICR is used in inverse dynamics to estimate joint torques, and it helps distinguish between normal and pathological movement patterns. This knowledge is essential for both rehabilitation and advanced biomechanical research. Uncommon method for locating the ICR involves motion capture systems like Vicon, OptiTrack, or Qualities. These systems track markers placed on the thigh and shank, allowing researchers to compute the velocity vectors of each marker. By drawing lines perpendicular to these velocity vectors, the intersection point reveals the ICR. If this intersection is near the knee, it indicates that the motion is primarily rotational. This approach provides a detailed and dynamic view of joint movement. Another accessible technique uses high-speed cameras and software like Kinematics or Tracker. By capturing two frames just milliseconds apart, researchers can identify 2 points on the shank and draw chords connecting their positions. Constructing perpendicular bisectors of these chords, the intersection point again gives the ICR. This method is similar to finding the center of a circle, and is particularly useful for quick, two-dimensional analyses outside of specialized labs. Inertial measurement units, or EMUs, such as those from Xsens, Norexen, or Delsi's, offer another way to locate the ICR. These devices are placed on the thigh and shank to capture angular velocities using gyroscopes. By applying the Rydberg equation V equals omega times r, researchers can solve for the position of the ICR. The advantage of EMUs is their ability to work in real-world environments, not just controlled laboratory settings. The highest accuracy, imaging techniques like fluoroscopy, MRI, or CT-based modeling are used. These methods track bone motion directly and build detailed 3D models of the knee. Computational tools then calculate the ICR, or the instantaneous helical axis, IHA. While these approaches are highly accurate and essential for prosthesis validation, they require specialized equipment and can be costly. Nonetheless, they provide unparalleled insight into knee biomechanics. As the knee extends, the path of the ICR can be visualized and tracked. This path isn't a straight line, instead it curves and shifts, reflecting the rolling and sliding mechanics of the joint. By studying this path, researchers can better understand how the knee accommodates different types of movement, and how these mechanics change in injury or disease. Such insights are vital for both clinical assessment and the design of supportive devices. Knee's movement is a combination of rolling and sliding. The ICR helps us distinguish between these two types of motion. When the ICR is close to the articular surface, the motion is mostly rolling. When it's farther away, sliding dominates. This distinction is important for understanding joint wear injury mechanisms and for designing implants that can withstand the stresses of daily activity. Engineers use knowledge of the ICR to design prosthetic and orthotic devices that closely mimic natural knee motion. By replicating the shifting center of rotation, these devices can provide more natural movement, greater comfort, and improved function for users. This application highlights the real-world impact of biomechanical research and the importance of understanding joint kinematics. Clinicians use ICR analysis to differentiate between normal and pathological joint motion. By comparing the path of the ICR in healthy and injured knees, they can identify abnormalities that may indicate ligament damage, cartilage wear, or other issues. This information is crucial for diagnosis, treatment planning, and monitoring rehabilitation progress. In biomechanics, inverse dynamics is a method used to estimate the forces and torques at joints during movement. The ICR plays a key role in these calculations as it defines the axis about which rotation occurs. Accurate identification of the ICR ensures that torque estimates are reliable, which is essential for both research and clinical applications. Vicon and OptiTrack are leading motion capture systems used in biomechanics labs worldwide. They provide high-precision tracking of body segments, enabling detailed analysis of joint kinematics, including the ICR. These systems are invaluable for both research and clinical studies, offering insights that drive innovation in prosthetics, orthotics, and rehabilitation. Innovia and Tracker are accessible software tools that allow for video-based motion analysis. These programs are particularly useful for educational purposes and small-scale research projects. By analyzing simple video footage, students and researchers can practice locating the ICR and gain hands-on experience with biomechanical analysis. EMUs are increasingly used outside the lab in real-world environments like sports fields or clinics. Their portability and ease of use make them ideal for monitoring joint motion during everyday activities. By providing continuous data on the ICR, EMUs help researchers and clinicians assess movement quality and detect potential issues early. Advanced imaging techniques like MRI and CT scans provide detailed views of the knee's internal structures. When combined with computational modeling, these images allow for precise calculation of the ICR and other biomechanical parameters. This level of detail is essential for designing implants and validating new surgical techniques. Help students grasp the concept. Imagine the ICR as a moving hinge point. As your knee bends and straightens, this hinge shifts, guiding the motion of your lower leg. This analogy makes it easier to visualize how the ICR's path reflects the knee's rolling and sliding mechanics, and why it's so important for engineers designing joint replacements. In summary, the instant center of rotation is a dynamic point that defines how our joints move, especially in complex structures like the knee. Understanding its path and behavior is essential for biomechanics, clinical assessment, and device design. Whether using motion capture, video analysis, EMUs, or advanced imaging, the goal remains the same: to replicate and support natural joint motion. By mastering the concept of the ICR, students and professionals alike can contribute to innovations that improve mobility and quality of life.